In this video, I'd like to walk you through how the authors solve example 8.9 in the textbook. In a previous video, I solved example 8.9 assuming that these two air track gliders hit each other and collided inelastically so that they stuck together. In this example, we want to work it out that the two gliders, maybe they have springs on their bumpers, collide and bounce off one another in a way that conserves kinetic energy. So I've drawn the before with glider A moving to the right at 2 meters per second and glider B moving to the left also at 2 meters per second. But the after is a little bit unpredictable. The gliders are going to hit one another and then they're going to bounce off. It's not immediately clear which way each of the gliders are going to be going. I mean, I might think something like this. If A was very much bigger than B, maybe afterwards they'd end up both moving to the right. Or if B was really a lot bigger than A, maybe afterwards they'd be both moving to the left. But their masses are pretty close and I'm kind of unsure about what will happen here. So when that happens, you just have to put in an unknown for the final velocities of each of the gliders and then let the math do its work. So for the after, I'm just going to put MA and I'm going to leave VA prime to be completely unknown. I don't know if it's left or right. And same for B. I'm going to put in that its velocity after the collision is also unknown. I don't know which way to put arrows. But when that happens, we have a sort of a math trick at our disposal. We can set up the equations and plug them in as positive numbers, and the math will tell us which way the gliders are moving. So since this happens on a frictionless air track and it happens pretty quickly, the initial and the final momenta have to be equal to one another. And that gives us a truth of this. It tells us that the momentum of glider A before the collision plus the momentum of glider B before the collision. Notice I said plus but wrote minus. It's to incorporate the fact that the velocity of glider B is to the left. So I'm putting the pluses and minuses in explicitly, and then for all the numbers I'm going to plug in positive values. Now afterwards, we're not sure what's going to happen, so we'll just leave these things to be unsigned quantities. One thing I want you to be aware of too is that I use the prime for after and the unprimed for before. The book does something a little bit different. I just find that this is a little bit easier for me to write. Now the thing about an elastic collision is that elastic collisions also conserve kinetic energy. So that would mean that the initial kinetic energy and the final kinetic energy are equal to one another. That would give us a pretty long expression, as a matter of fact. It would tell us 1/2 ma VA squared plus 1/2 mb VB squared has to equal 1/2 ma VA prime squared plus 1/2 mb VB prime squared. And you would be left with two equations to solve for two unknowns. The problem is it's pretty difficult to unravel these two equations and two unknowns when in one of them all the v's are squared and in another one all the v's are not squared. So as a consequence, for perfectly elastic collisions, there's a trick that we can incorporate that's written about in the book on page 234. Now before I tell you the trick, I do want to call your attention to the fact that there are some equations in the book in section 8.4 about elastic collisions, equations 11 and 12, and you might be tempted to use them here. The problem is equations 11 and 12 only work when one of the masses is initially at rest, which is not the case in this problem. They're both moving. So we can't use equations 11 and 12 if you want to look at them. We have to start from scratch. So we have one truth of the system and we need another one. The second truth comes from conservation of kinetic energy, but that's a little bit difficult to unravel. But the trick, which is written about on page 234, is something about relative velocities. It turns out that the rate at which these two masses are getting closer to one another before the collision is going to be equal to this rate or the speed at which the masses are moving away from each other after the collision. So the relative velocity between A and B is the same, but in the opposite direction after the collision compared to before. And the way that we can write that into an equation is to simply write something like this. So there's the relative velocity after the collision, B minus A. It's going to be the same as the relative velocity before the collision, but in the other way. So this is the relative velocity after the collision. This is minus the relative velocity before the collision. So we can use this as our second truth. And really what we end up with are two equations and two unknowns, which we have to solve simultaneously. So while normally I approach these things in an algebraic way, I think that we'll just use numbers this time around. So the thing I want you to notice is that this thing here evaluates to a number. We have MA and VA. We have MB and VB. These are the numbers here. So if you just evaluate those two numbers, you end up with 0.4. Now the units are kilogram meter per second because those are both momenta. And on the right hand side of this, you'd have the mass of A, which is 0.5. And you got the mass of B, so that's good. The other thing that we know is we know what VA minus VB is. So VA is plus 2 meters per second minus VB, but VB is minus 2 meters per second. From that one, we know that VB prime minus VA prime is equal to 4.0 meters per second. It's a little bit of a trick here. VA minus VB, since VB, the velocity of glider B before the collision, is to the left, we have to make that negative there. So here's what we got. We have two equations and two unknowns that we would like to solve simultaneously for the velocity of A after the collision and the velocity of B after the collision. So I'll step you through this, although it might be kind of boring. Here's going to be my first step. I'm going to stop writing the units for things, and maybe that will simplify things a little bit. So I need this. So that's equation 1 written without the units. And here's another thing to think of. I can solve equation 2 for VB prime. I can just plug in the fact that VB prime is going to be equal to 4 plus VA prime. That way, I could substitute that into here and I would eliminate VB prime. So let's write that down. So working on equation 2 here, great. So there's our equations 1 and 2 rewritten. I think it's pretty easy to see what you're going to do. Take this, which is VB, and put it here, and do a little bit of algebra. All right, so I'm going to do it quietly here so I don't make any mistakes, and you try to catch me in my errors if I make one. So all I did there, I didn't skip any steps. I just substituted this expression for VB prime into there. Now I'm just pushing symbols carefully around a page trying not to make any mistakes. So here I distributed the 0.3, so 0.3 times 4 is 1.2, and 0.3 times VA prime, that's it. So now I just got to combine like terms and simplify it. So let's see, I got this and this, these are constant terms, and I got 0.5 and 0.3 VA. Let's see, how would I do it? Let's subtract this over to the other side. So I would do 0.4 minus 1.2, and that would give me minus 0.8. That's taking care of this and this. And on the right-hand side, I have 0.5 plus 0.3 is 0.8. And finally, I can solve the damn thing. Looks like VA prime, going to divide both sides by 0.8, is minus 1.0 meter per second. And then if I want to know what VB prime is, well, I can just plug it into the equation here. Since VB prime is 4 plus VA prime, that makes VB prime equal to 3.0 meters per second. So to wrap this up, we'll just summarize what we got here. We find that the velocity of the first glider after the collision, if we do the math, comes out to be minus 1 meter per second, but we interpret that to mean that that glider is moving to the left. And B, it ends up moving to the right because it came out positive at 3 meters per second. So that's exactly the way the problem is solved in the book. And additionally, the example in the book goes on to verify that the kinetic energy before and after are equal. And also call your attention to the fact that there's a practice problem at the end of this example, which would be great practice for you because it's a similar problem and the answers are given.